Hi, so today's video is going to be about differentiating the function arsinh or r hyperbolic sine of 1 over x. So that's what we want to do in today's video. Again, it's just worth noting, like previous similar videos to this, where we've got this 1 over x as a variable. So it's worth noting that x can't be equal to 0 because you can't have 1 divided by 0. That's not defined. And in fact, let's just check more information about the domain and range of this function here. And we can do that by sketching the arsinh function. So this is something that we've done. Well, I don't think we've actually done this before, but let's just sketch this function here. So the inverse sinh function. So we know the sinh function. I'll do this in blue. So the sinh function kind of goes something like this. So the inverse of that function, so just reflecting that function in the line y equals x, you get something which looks like this if we do that. So let me just sketch the arsinh function. So the arsinh function is going to kind of go like this. Sorry, let me do that a bit neater through the origin and like that. So yeah, so as x tends to infinity, arsinh actually still tends to infinity, and as x tends to negative infinity, arsinh still tends to negative infinity as well. So what we can tell from this is that the domain is just x in the real numbers. So every x value, every real value that you put into the arsinh function is defined, and also the range is the real numbers too. So the range is x in the real numbers. Okay, so we know that then. So if we just consider the domain and range now of the arsinh of 1 over x function, so the domain of let's just write it down here. So therefore, arsinh of x. So the domain is going to be, sorry, I've made the mistake here. This should be arsinh of 1 over x. So for this arsinh of 1 over x function, the domain is going to be, well, all 1 over x values in the real numbers just by swapping this variable with this variable. And if 1 over x is a real number, then it must be true that x is not equal to 0. So any real number apart from 0 is in our domain. And our range for this function, so again, it's just the same as this over there. So the arsinh function always has a range of x in the real numbers, regardless of what variable we put inside that arsinh function. Sorry, the arsinh of, it's whatever variable we put inside the arsinh function. Yeah. So we know those two facts there. Okay, so we can now go on and differentiate what we want to do in this video. So this function here. So by differentiating arsinh of 1 over x with respect to x. So again, you'll probably notice that this is a chain rule problem. We're differentiating a function arsinh of a function, the reciprocal function of a function of x, sorry, which is a function of x. So this is going to be the chain rule. So using our chain rule formula, we would get this. So we're going to differentiate the arsinh of 1 over x with respect to 1 over x. And then we're going to multiply this by the derivative of the 1 over x, but with respect to the variable x. So yeah, again, this is just by using the chain rule. If you're not sure how to use the chain rule, I've done lots of previous examples using it, and I've even got a video where I proved the chain rule. So yeah, you can go and check out those videos if you're not sure how I've done that. So yeah, we get the chain rule here. And now to differentiate this first part, so to do this first derivative, we're going to need some knowledge on differentiating the arsinh function. And we've done this in a previous video. So we know that when we differentiate, actually, let me go to a new slide. So we know that when we differentiate with respect to x, the arsinh of x function, this was the result that we got. So we got 1 over the square root of 1 plus x squared. And the arsinh function, as we've seen, is defined for all x in the real numbers from the graph that we drew. Graph that we drew back here. So that was our result from that video when we differentiate arsinh of x. But we don't want to differentiate arsinh of x with respect to x. We want to differentiate arsinh of 1 over x with respect to 1 over x. So we can just swap the variables around. So this x there becomes a 1 over x. This x inside there becomes a 1 over x. And that would therefore mean that this x over there becomes a 1 over x, like so. And again, we can just simplify the result we get at the bottom there. So this is just the same as 1 over the square root of 1. So 1 plus 1 over x squared. And in fact, I'm just going to tidy this up a little bit more. So we've got 1 over, so the square root of 1 over x squared. If I just take out a factor of 1 over x squared from that part there, we're going to get x squared plus 1 like that. And so as a consequence, what we therefore get is we get 1 over, so the square root of 1 over x squared, well, that's just going to be 1 over the square root of x squared multiplied by the square root of x squared plus 1. But we know that by definition, the modulus of x is defined to be the square root of x squared. And so this square root of x squared in the result is just the modulus of x. So 1 over the modulus of x, and that's multiplied by the square root of x squared plus 1. Okay, so that's what happens when we differentiate our sinh of 1 over x with respect to 1 over x. So yeah, we get 1 over the modulus of x multiplied by the square root of x squared plus 1. And when we differentiate this second part, so we're differentiating x to the power of minus 1 with respect to x. So we've done this plenty of times before. So we're just going to get negative 1 over x squared like that. And again, I've got previous videos where I've done a similar thing with that. Okay, great. So now we can just tidy up the fraction multiplication. So what we're going to get, so top times top, we get negative 1, and bottom times bottom, we get an x squared over the modulus of x multiplied by the square root of x squared plus 1 like that. But again, what we know, so we know that when you divide x squared by the modulus of x, well, that's just going to get us the modulus of x, because the modulus of x squared is the same as x squared. So this on the bottom is just going to be a modulus of x, so minus 1 over the absolute value of x multiplied by the square root of x squared plus 1 like so. And so what we can conclude then is that, well, we know the domain of this arsinh function is all x values apart from 0. And so we've got the derivative there. So what we can say then is that the derivative of arsinh of x is equal to, so as we got back here, so negative, sorry, Have I forgot a negative? Oh no, I've got the negative there, sorry, my bad. So yeah, it's going to be negative 1 over the modulus of x multiplied by the square root of 1 plus x, like so. So that's the result. Oh, sorry, I've made a mistake again. Sorry, this should be 1 over x in there. Yep. So the derivative with respect to x of arsinh of 1 over x is this this result there. Now, if you saw the previous video, you'll probably notice something. So in the previous video, we differentiated the r cosec of x function. And when we differentiated that function, the result that we got was also the same. So negative 1 over the modulus of x multiplied by the square root of x squared plus 1. I would just write it the other way around, so 1 plus x squared inside that square root. Okay, so we got the same result. So the question really becomes now, so are these two functions here and here, are they the same? So I'll put a question mark there. In fact, they actually are, and we can just show that by checking that they have the same domain and then just doing some algebraic manipulation. So do these two functions have the same domain? So we know that this domain for the arsinh function was all real numbers apart from 0. So all real numbers apart from 0 is our domain. What was the domain of the r cosec function? So we sketched this graph in the previous video. So the r cosec function kind of looks something roughly like this. If we sketch a graph of r cosec of x, you get something roughly like this. You get an asymptote at x equals 0, and you get an asymptote at x equals 0 and y equals 0 as well. So something kind of like this. So that's the r cosec graph. And as we can see here, the domain, well, we can have every real value of x in the domain. So, well, sorry, we can have every real value of x apart from 0, which will give us a defined r cosec function. So the domain, again, is just x not equal to 0. So yeah, that is our domain. And it's exactly the same domain as the arsinh of 1 over x function. So they've got the same domain, they've got the same derivative. So therefore, it must be true that arsinh of 1 over x is the same as our cosec of x up to a constant. In fact, this constant is actually 0, and we're going to show that now. But we know from just this slide here that this must be true there. So let's go and show that these two functions are actually the same. So what we can do is we can let y be equal to cosec of x. So what we can do now is apply this. We can apply the inverse of the r cosec. Sorry, this shouldn't be cosec. This should be r cosec. My bad. So this is r cosec of x. So we can apply the cosec function to both sides. So apply cosec of y to that side, and then apply cosec of r cosec of x to the right side. And as you'll notice, so cosec and r cosec, they're inverse functions. So we're applying the function of its inverse to a variable x. So we're just going to get the variable x on the right side. So therefore, cosec of y is equal to x. We know by definition the definition of cosec. So we know cosec is just the same as 1 over hyperbolic sine by definition of what cosec is. So you've got 1 over hyperbolic sine equals x. And so therefore, what we can say from this is that sinh or sine or hyperbolic sine, however you like to say it, is equal to 1 over x. We could apply the arsinh function, the inverse sinh function, to both sides. And you may think, yeah, that's fine, we can do that. But we've got to check first that we're allowed to do this. And that's because, so on this left-hand side, we've got y inside the sinh function. Y is not a variable. So y is a function of x, namely the r cosec of x function. So similar to previous videos where I differentiated arctan of 1 over x, or arcsine of 1 over x, or arccos of 1 over x, we've got to be careful here. Just because this is not a variable, this y is not a variable, it's a function. So we need to check, do the y values, or do all of the potential y values, are they contained within the domain of this sinh function? And in other words, is the range of this y function contained within the range of this arsinh function? So we need to check. So need to check is range of y a subset of the domain of the sinh function, but the domain of a function is the same as the range of its inverse function. So this is just the same as the range of the arsinh function. Okay, so we know the range of the arsinh function because we sketched that back over here. So the range is x in the real numbers. Okay, so let's write this here. So the arsinh function, so range of arsinh, so that is just it's just all real numbers. And the range of y, so the range of this cosec of x, so we sketched this graph back here. So the range again is all real numbers. I mean, technically r cosec of x can never be equal to 0. But it doesn't really matter. I mean, we could just put range is not equal to 0. So you can just put here that the range of y, so y is the same as cosec of x. So the range of y is just equal to the real numbers. But as we can see from the graph, it won't ever be equal to 0. So we could just put a not equal to 0 in there if we wanted to. So what can we see? Well, the range of y, this real numbers apart from 0, is contained within the set of the full real numbers, because this real set is a subset of the entire real set of numbers. And so therefore, it is true that we can use this R-sinh function on both sides of the equation, because it will be defined. So let's just write that down here. So therefore, this is true. So range of y is contained within range of the R-sinh function. And so therefore, this R-sinh of y is defined. And so therefore, this just becomes a y there. Okay, so we know that therefore y equals R-sinh of 1 over x, like so. But we know, okay, so we know that's true, but we know that y is the same as r cosec of x. So therefore, it has to be true. Sorry, let me just move this g back up to where it was. Just okay, so we know for a fact then that it must be true that r cosec of x is equal to the function r-sinh of 1 over x. And so therefore, it's no surprise that they have the same derivative, because they're defined on the same domain, as we can see there and there. They've got the same derivative, and clearly they are the same function, as we've just shown there. So therefore, the conclusion from today is that when you differentiate the r-sinh of 1 over x function, you get exactly the same result as differentiating the r cosec of x function, and that result was this result here, so -1 over the modulus of x multiplied by 1 plus x squared, like that. And that's the end of this video.